Welcome to Spring LIB.
Problem, we have a circuit consists of a 12-volt battery, a capacitor C, and a resistor of 20 mega ohms. Now, at time 2, we throw the switch, it's flowing, and we start charging the capacitor. The electric field between the plates is given as uniform. Now, at time t is equal to 250 microseconds, we are required to find out the magnitude of the magnetic field at a radial distance of 3. So let's start noting down certain things. So we'll draw the parallel plate capacitors. Imagine these are the plates of the capacitor. These are the two leads. It is 5 centimeter. So capital R is 5 centimeter. We need to find out the magnetic field at section which is at a distance of 3 centimeter. Separation between the plates is about, so T in this case is roughly about millimeters. So T is equal to 3 millimeters. So we begin by first finding out the capacitance. So let's find out the capacitance of this. Now that is given by the formula for a parallel plate capacitors as epsilon naught A over D. And A in this case is pi. A mere substitution 2.318 10 power 11 2.318 10 power minus 11 farads. Now we need to find out the magnetic field at a radius of 3. So if this is 5 overall, the 3 should be somewhere at least this much. And let's take the center from the center. This is 3 millimeter. If this is from the center, if this side is 5, this could be 3 meters. So we start with the Ampere's law. So again, we have a P dot dl, and instead of, because there's no actual current, we have to take care of what we call as the displacement current ID, and a closed loop. Now in this case, the displacement current that we have should be to the overall displacement current, overall displacement current, and the displacement current here should actually be equal to the current which is actually flowing through the wires. There is no real current here, but what we have is called the displacement current, the magnitude of which is exactly equal to I. So there is a certain current I which is flowing here. So I can say the displacement current here is I. However, the current flowing only through this much of radius. So then we have to take care of the area. So that proportion is pi r square, area of that much section, divided by the area of the entire plate which we have. Okay, and so the P, or the magnetic field in this case, is given as mu naught, the current I which is flowing in the wires at a certain given at t equal to 2 seconds. Pi and pi gets cancelled out. From the TL integral of pi, small equation is now r divided by 2 pi capital R square. Since we know all the terms in this equation except for I, we now start what is I. So we have found out what is the capacity and we are. So our next step should be to find out time constant. So the time constant RC for our circuit is, when we get 636 10 power minus, so 4.6 0.36 per minus 4 seconds. This is a really small value. And also know that the current I in the circuit actually goes down, so which is given by as V over R into e power minus T over RC. T is 12, so let's put a value of 12 volts divided by 20 mega ohm. And for our special case, we have this is minus of T, which is 250 microseconds. All of that gets divided by 4. I can also write this number in terms of the microseconds, so that is equal to 463.6 microseconds. And this ultimately leads us to a value of 3.5 into 10 power 7. And we see that by after 250 microseconds, the current has actually reduced to a very there because R is actually very large. So the current initially was also very small. And thus the magnetic field which we have due to the current which we have, displacement current is mu naught I. This I is same as the I we have here. In all the numbers, 8.4 into 10 power minus 13 Tesla. So this is how most of our approaches should be. We should first write down what we know, and then from there find out all the other variables that we need to determine. So we saw, we first calculated C, wrote down our equation, found out that we need to find B, and in that we need I. Then we went about finding out what is I at that point in the wires. The I within the wire is actually also equal to the displacement current at all the times. So then we solved the question.